Hi there, welcome to another presentation of our e-tutorials. My name is Charles Wasfan Msipa. Our discussion today is on integrating transcendental functions. In this case, we're talking about functions like sine, there's trigonometric functions and exponential functions. So I'm going to use here one or two trigonometric functions as examples and parallel that explanation with similar examples of exponential functions, hoping that you'll be able to generalize that to the rest of the transcendental functions. Let's start this way. We have this familiar table by now. We've got an example of a transcendental function, sine x, and we've got different variants of them, and having a c representing each of the constants, noting that here the constant is 0. So we know that if we differentiate this function, we are following our way of differentiation. We'll call upon the immediate derivative of sine, which is in this case cos sine, and we'll retain the argument x, and we'll multiply by the derivative of the argument dx, which we usually don't write because it's a 1, but I'm repeating it here so that we keep on systematizing that idea that when we're differentiating a function, we always somehow apply the chain rule by calling upon the immediate derivative of function, retaining the argument, multiplying by the derivative of argument, which normally we just write as cosine x. So now, having this, like we've done here, we've done differentiation. Like we said before, integration would be asking us that we're having in the presence of a derivative which is cosine x with respect to x, then we need to answer this question by giving the function which, when differentiated, give us this function under integral sign. In this case, clearly here, it's going to be sine x. Now, remembering that this derivative does not only come from sine x, it could be from sine x plus 0, sine x plus 4, or sine x plus that, or any other constant. Then we write here that the integral of cos, now the function which differentiates to cos x is sine x plus a constant c, a real number. In this case, standing for any constant which will be added to that function. Now, I hope that is clear. Now, proceeding, we can do that exactly the same kind of analysis of the function like this. And we know that the derivative of e to the power x is e to the power x. And this is a derivative, could be a derivative of e to the power x plus c, or e to the power x plus 3 pi over 7, or e to the power x plus 8, or even e to the power x plus 0. So now, this function is actually a very interesting function because when you differentiate it, or when you integrate it, it comes exactly as it is. And usually, depending on the argument, it will come multiplied by the derivative of the argument. In this case here, the derivative of argument will be dx with respect to x, which is actually, this is equal to 1. Then we don't usually write that and just write simply e to the power x. So coming to integration, this is what we're given as integral e to the power x. Now as we're in the presence of a derivative with respect to x, then we are being asked to find the function which differentiates that, which is obviously, as you know, is e to the power x. Now, as an answer to integral, this is not enough. We have to go to consider the different constants can be added to that function. Then we get that plus c. So now, proceeding, what we're going to do now, let's look at a bit more challenging type of function. Let's say we're given this. We know that when we differentiate this, we're going to use exactly the same principle. Call upon the immediate derivative of sine, which is cos 2x, because we have to retain the argument, multiplied by the derivative of the argument, which is 2x with respect to x. And we know that simplifying this will come up as 2 cos 2x. So obviously, if we take this and put it under integral sign, every one of us will be able to answer the question and say sine 2x. But in some cases, we meet these successes as given like this, cos 2x. At this stage, you can see that we will copy the derivative exactly as it is, and that is what you must expect in exercises. We're not going to be given complete derivatives, but maybe parts of the derivative, and you need to complete the missing information before you can integrate. So in this case, when we put this, we note that this type of question will be given, for example, like integral of cos 2x dx. Now, if we look at this expression, we will actually copy the derivative exactly as it is like in the previous case. These are the type of challenges you're going to be given. You'll be given some part of the information, complete information, then you are supposed to analyze and complete the missing information in order to be able to integrate. In this case here, we cannot say that the integral of this is sine 2x. Why? Because this is not a complete derivative. Now let's see what kind of manipulation we can do in order to do this. Let me leave this here. This is not equal to that. Let's do that. Then let's copy again this and say cosine 2x dx. Now here I want to discuss with you how we're going to one way of handling this kind of a problem. Now this is not a immediate derivative, but we know that when we are differentiating, when we're finding a derivative, we always need to have also the derivative of the argument. So now if you look at this function and assume that it is a derivative from sine 2x, you can clearly see that there's a derivative missing here, which is 2. So to compensate for that, we'll sometimes do this transformation. We write the 2 over 2 cosine 2x dx. By writing that, I'm trying to get to a situation where this really looks like a derivative, but I'm introducing here a 1, which is given in some kind of a clever way as 2 over 2, which is equals to 1. So in the next step, we'll then take 1 over 2 as a constant out of the integral sign because it's redundant there, and leave this 2 as 2 cosine 2x dx. So by doing this kind of transformation, this is still equal to that because we multiplied only by 1 here, and now by rearranging this, the equality still holds. Then now what we have under integral sign now is a complete derivative, whereby we've got cos as an immediate derivative of sine, and the 2 as a derivative of the argument. Then we would now integrate that as sine 2x multiplied by this half, which will come up with as sine divided by 2, sine 2x divided by 2 plus sc. Then this becomes the integral of this function. And you can verify that by differentiating this and see whether you arrive exactly at this kind of an expression. Nextly, we can now take this kind of similar discussion to an exponential form of a function. In this case, we've got something like this. We've got f of x is equal to e to the power 2x, and you will see that you can do exactly the same kind of analysis. Note here that e to the power 2x is actually encoding something which we write as exp to x. In this case, this is just an indication that we're doing an exponential function like sine 2x. The word sine there was telling us that we're dealing with a trigonometric function. So now, the way we would do this with the differentiation, we would call upon the immediate derivative of e, of course, exponential function e, which is e, and retain the argument, which is 2x, and then multiply it by the derivative of the argument. The argument in this case is 2x, differentiated with respect to x. Now, if we take this back to integration, you will see that it will work out exactly or similarly to what you've seen with the trigonometric function, and I would like to invite you to experiment that on your own without further discussion led by me. So let's proceed to the next set of trigonometric function, which is this one. In this case, you can see that now the power is changed to 2, and then looking at what will happen when we deal with x to the power 1, x to the power 2, now looking at x power 3, we must try to generalize this to a situation whereby we've got the sine x to the power n plus c, and see how it happens. So in this case here, what would happen actually, we would get derivative of sine in cos sine, and they will retain the argument, which is x cubed, and all the constants 0, 90, cos of 5 pi over 2, and in general c will be 0, then this will be multiplied by the derivative of the argument, in this case the derivative of x cubed with respect to x. We know this is going to come up as 3x squared cosine returning argument x cubed plus 0 constant, but we're going to look at this as that. Now, like I said before, the derivative is not going to be given this way in a complete way, but that we could have this problem given as integral of x squared cosine x to the power 3 dx. So now it will be up to you who is presented with this exercise to now analyze that if this is a derivative, a immediate derivative to immediate derivative of sine, and that sine would have the same kind of argument, then you must try to check what kind of function must be accompanying this derivative here. Definitely it should be the derivative of this argument, and which we know that the derivative of this argument will be 3x to that, but in that case we will not be having our 3x's we are given there. So what we do, we now need to transform this to look exactly like a derivative of a sine of x to the power n, in this case n being 3. So what would you do? We'll do exactly a similar transformation like before. What we have here, we'll say integral, then we'll say x squared cosine x cubed dx. Now transforming this to a derivative, we need a 3 here, but if we write a 3 here, then we'll offset the equality. So what we're going to do, we write a special 1 here. Our 1 is going to be 3 over 3, which is equals to 1. Then we write there 3 over 3. Now we see that the 1/3 here is not forming part of the derivative. Then, like we know, we can take it outside integral sign as 1/3, and then we remain here with 3x squared, which is the derivative of this argument, multiplied by cosine x cubed dx. Now having that, now we can see now that we've got a complete derivative. Now we can now integrate that, and definitely the answer would be something which is called this kind of a function. So we would have this as equals to, this will be derivative coming from sine x cubed. So we write here sine x cubed multiplied by 1/3, which is the same as dividing by 3, and then plus a c, which represents n of the constant which could be added to that function there. Now, if you check this now, you can start systematizing this and check what happens from there, from this point to there. It looks, if you analyze properly, it looks like it's simple calling upon the antiderivative of the function, which is here, in this case, which is sine, retaining the same argument, and then dividing by 3. But that's how it looks apparently, but you should understand that this is a process, there's been a process here of compensating this deficient derivative here this way until we come to this conclusion. And later we're going to look at another approach, which in this case is called methods of substitution, for the purpose of doing exactly the same thing. So now lastly, now you can take this kind of discussion to a situation like this and try to engage with this situation in a similar fashion, in such a way that at the end of that you can be able to do both trigonometric functions and exponential functions with different arguments, powers of x, or even when we've got something like e to the power x cubed plus maybe let's say constant, you should be able to see that this will still work more or less like we have there. But for now, engage yourself with this and take the experience from the previous discussion and try to see that you understand how to do the following integration. In this case here, we know that we'll be integrating, and there's a derivative which is either exactly derivative of this function or some kind of a deficient derivative, which we need to compensate like we've seen in the previous example, and proceed with our solving of problems. For now, thank you for listening. Meet you in the next discussion.